I'm Jason Timmins. I'm the Technical Director of MBM. We're a small MSP. My day-to-day work is really, can I fix Sylvia's printer and accounts? Why didn't Dave's email go? Day-to-day IT support things. But we're a Microsoft house, of course, 365 and Azure. It never hurts to learn new things. So I did the Microsoft Learn courses on Azure, on Azure Quantum last year. Thought I'd take a step into speaking. Bought a clicker, which means I'm a speaker now. So if there are any quantum computing experts in the room, then I perhaps haven't grasped it fully. But here we go. Let's give it a go. There's an agenda. It'll be roughly speaking like that. Quantum computing holds some radical possibilities to improve our lives around agriculture and climate change and material science, that sort of thing, tackling problems that are really hard for current computers to deal with. We'll see in a minute that we're at the beginning of this, both from an Azure perspective and general quantum computing. Azure Quantum is an open platform that allows Microsoft to run your quantum workloads in much the same way as you run your traditional computing workloads. Microsoft don't yet have any skin in the game in terms of quantum hardware. Others do, and they're available to use inside Azure Quantum. And we'll see a bit of that later. With the wind in the right direction, it will need to be, or try and run some actual quantum code on an actual quantum computer. Don't hold your breath. You'll see in a minute why it's not an exact science. Quantum computers work very well at solving sort of nutty mathematical problems, really tricky mathematical problems, things like simulating molecules and the folding of molecules and all that sort of stuff to try and find great catalysts, new fertilizers, better drugs, that sort of thing. I'm led to believe we can now make molecules, but getting them to work in the way that we want them to work is a very, very hard problem. Quantum computing can be involved in that. Cryptography or uncryptography, you see what I mean? We'll come back to that in a minute. Machine learning can help with that too. Quantum computing can help train models, test models, that sort of thing. There's a bit later where we talk about how that can mix, but quite good at search problems. If you've got a massive problem space that you need to address, then quantum computers can search for the best solution across that. In some models, you can almost view it as like a 3D landscape where the best solution is the lowest valley across this entire landscape, and rolling a ball off one mountain and just down until it stops is not necessarily the best solution. The next valley over could be a better solution. Quantum computers can help achieve that instead of just running randomly across the space. So let's talk about classical computing. As you can see, this machine has got everything you could possibly need. It's got a CD rewriter, it's got a floppy drive, it's got a PS2 keyboard, it's got a great screen. It's got those speakers that tell you when your mobile phone's about to ring. Perhaps there's PS2 ports at the back, who knows? That's a classical computer. This is a quantum computer. This is Microsoft's quantum computer. All the action occurs down here at close to absolute zero. So quantum computers have to be cooled radically in order for the quantum effects to manifest themselves. This is with it open. Usually it's covered in a large sort of metal tube, rather like an immersion heater in your airing cupboard, which is filled with liquid helium and is chilled and chilled and chilled. And it gets colder and colder the further you go down till it's literally fractions of a degree from absolute zero at the bottom. And at the top, I like to think it's the temperature of a nice gin and tonic, but who knows? That was Microsoft. They are obviously a trillion dollar corporation, so they have a gold one. This is from a university. They've got a rectangular one made of copper, and it gets colder and colder as they go towards the center. No, there isn't. You can kind of put your arms around them. It's that sort of thing. But this is IBM's quantum computers. Arguably, IBM are the leader in quantum computing at the moment. You can see these are more like pipes and waveguides than wires. This is really open, of course. This is what it looks like closed. This is something you can buy. This is IBM's first quantum computer. It's called a QS1, Quantum System 1. As we know, they do like those abbreviations. PS2, AS400, RS6000, QS1. Now, I think IBM have been pretty shrewd here. What they've done is made it very shiny. And the people who sign off the checks necessary to buy these things do love shiny things, watches, jewelry, cars, yachts, airplanes. And frankly, if that was in our business, we'd put it in reception because they've made it beautiful. Then people would come in and we'd be able to say, this is our quantum computer. And they'd say, what do you use it for? And I'd say, let's not worry about that. Let's get you a coffee. Now, quantum computers are measured in the number of physical qubits they have inside. So we have modern computers, 64 bits binary digits, yeah. With quantum computers, it's quantum digits, qubits. This has got 48 qubits in it, working qubits in it. This is quantum system 2, or at least a rendering of what it's going to look like. In the video, they had this is sort of a, this sort of computer rack height, yeah. In the video, they had, it's like a football field sized data center full of these things that extend through the ceiling. And so there we go. That's what they were. That's
correlation between how powerful it is and how bright it is.
Yeah, it's crazy, isn't it? I don't know. They're always a bit dark and sinister, wasn't it? But they seem to lighten it up a bit. This is a quantum computer from a TV series. So this one doesn't exist. This is from a TV series called Devs on the BBC, which if you're in IT, you might want to look at. It's pretty cool. Here in the program, they made a quantum computer that was so powerful that they could simulate the entire universe in it. And because as is a clockwork universe, allegedly, they could dial it forwards to predict the future, and they could dial it backwards to predict the past. And in the end, the company's charismatic leader copies his mind into the quantum computer and lives in a quantum world. Now, by buying a server, we all know about, right? We all know how to buy a server. We look at the spec sheet. So this is a spec sheet for a quantum computer that you can buy today from Quantum, and you look down here and you see all the specs. And you think, oh yeah, fair enough. I'm covering some of these things. Table of contents. Features, Honeywell, it's part of Honeywell Corporation, these guys. It's a bit more complicated, yeah, okay, yeah. Processors, yeah. Hardware nomenclature, oh yeah, okay, well, no. Things start to get a bit more involved now. A bit more maths, a bit more science. Oh yeah, okay. Oh, that's good, look at that. Quantum computing is basically about matrix mathematics and complex numbers and radians and other stuff like that. Yeah, it gets a bit involved. We are kind of very much at the early stage of quantum computers, and they're all different. So in a world where there were no IBM PCs back in the olden days, there's no standards at the moment anyway around quantum computers. So they're all different. They all do different things. You have to be a special sort of person to consider buying one and owning one. This is a classical program. You do one thing, you do another thing, go back around. Some of you of an older generation might recognise this. Anyone recognise what the semicolon means at the end of a print statement in BBC Basic? Well, yeah, any idiot can write Kev is cool down the screen, but it takes a badass to write it all over. It bothers me intensely that the wonderful BBC Micro is now rendered in a web browser in Java, but never mind, what can you do? So, classical program, do one thing, do the next thing. That is a quantum algorithm, quantum circuit represented in a format. These are different sorts of qubits. There's a plus, I recognise a plus. You need to understand this sort of stuff to get good value out of a quantum computer. This is called Hadamard test, and the scientific paper I got it from described it as very simple. These are the sort of people that you need to program a quantum computer. In Microsoft's world, you program quantum computers using Python or Q#. Q# is a domain-specific language for writing quantum algorithms. It's a Microsoft-style sharp language, so it's in all the development environments, it's in all the source control and stuff like that. Now, a quantum computer is, as you saw from the previous examples, it's got no USB, it's got no VGA port, it's got nowhere to plug a keyboard. It's not like that. It is a coprocessor that exists next to a classical computer. The classical computer feeds it, and the results come back to the classical computer. The quantum computer cannot talk to SQL Server, it doesn't know about connection strings, it can't open APIs, it has no concept of that at all. And quantum computers are wildly unreliable. So in order to get any sensible results out of them, you have to run the process again and again and again. Sometimes you get plus infinity, sometimes you get negative infinity, sometimes you get 0, sometimes you get 38. 38 might be the number you're looking for, but you get all this noise as well. So you have to run it again and again and again, and then build an average of the results. And hopefully, peak of the curve is the result you're after. You call it shots in the terminology. So you can anything from 50 to 500 times you have to run your algorithm again and again. So it's very costly in terms of getting stuff done. Estimation is important. You can knock up an algorithm, quantum circuit, and it's quite easy to end up with an algorithm that can't run on any current quantum computer. So the estimation will tell you how many qubits you need on your computer and how long it's going to take. So it's vital to do an estimation. This is Microsoft's programming model for quantum computers. So over here is your desktop machine where you do the application development and you run a simulator and you try and get at least some working code, which is two parts. There's a classical part. This is the part that speaks to APIs and SQL and all that. And this is the quantum circuit that you've built that takes the data, thinks about it, sends it back to the classical loop, and it goes round and round and round. I kind of thought that you would build a quantum program, you put it into the quantum computer, and then hit run, and an instant later it would give you the result. It's not quite like that. You have to keep throwing data at it, keep doing it again and again, and there are long run times for quantum programs. So the state of quantum computing is rather like this. This is Colossus from 1943. This is a computer that was down at Bletchley Park back in the day. Still down there at the Museum of Computing. They rebuilt it. So you can go and see it if you like. The program runs on a paper tape around the thing, and undoubtedly it did useful work. But it was small, hard to program, hard to use, hard to build. And that's kind of where we are now, as far as quantum computers are concerned. This is Intel's first ever microprocessor, 4004. This was a 4-bit processor, 50 years old admittedly, but a 4-bit processor. The largest number you could deal with was 0 to 15. If you wanted to add anything more than that, or a result that was anything more than that, you had an overflow, and then you had to deal with the next bit of the number. So it was rather like doing additions in primary school on the chalkboard. You'd have 1,000 number here and a 2,000 number here, and you'd add them up, and you do carry the 1, add this column, carry the 2, add the 1. Yeah, so you could get things done with that, no question. And it was in an earlier calculator. It was laborious. You had to write lots of code. It took a long time to get anything done. 2,300 transistors in here. Current Intel processors, maybe 22 billion. Now we're 50 years on. I suspect that we'll see way more qubits than 48. So we've got here this is a slide I stole from Microsoft. These are various quantum things you might want to do on a quantum computer. I honestly forget what quantum dynamics means, but okay. Chemistry would require, this is finding, the right material to join to another material. 2,700 logical qubits. Factoring, which is the encryption thing, 25,000 qubits. So computers of that sort don't exist yet. This graph here is the number of qubits in your computer, physical qubits this time. That's 1 million on the dotted line. And across here is the runtime, from seconds, centuries. So if you've got 1 million qubit machine, that's where it starts to kick in, where you can start to get stuff done in a sensible time scale. You want 10 million qubits here to do factoring, and you can do that in a day. And chemistry might take months. But if you think that you're trying to find a catalyst that could pull carbon dioxide from the air and turn it into oxygen and carbon, you could undo climate change. That catalyst would be worth trillions. Quantum computers are small and primitive in the same way that the chips in the Colossus machine we just saw, hard to get stuff done. They're slow in the sense of getting a program into them, because what you're doing is arranging quantum structures at the very bottom of that of those golden machines, and then you have to send data down, and it has to think about it and send the results back. And you have to reach down through all those layers, through all those little pipes and tubes and waveguides and what have you, get things done. So that part is slow. I think the actual part of the quantum part is hamstrung by how slow those are. As we've seen, hard to program. You have to be essentially a scientist, let's face it. And they're unreliable because the quantum structures that are built at the bottom of those golden machines are very susceptible to any form of interference, whatever, from one another, even from a gamma ray coming through, smashing the thing to pieces, to it being, a tenth of a degree warmer than it should be above absolute zero. They're very unreliable. Very rare. So there's no skills around, and they're hard to get. They're expensive to buy, expensive to use. No, they're not too expensive, but if you're doing long run times, then it can get expensive. Expensive staff. You need scientists and physicists and very skilled people in order to get the value from them. And notwithstanding, if you're an enterprise that's dealing in materials or financial services and things, then you've got skilled staff. And Azure Quantum, the cloud service that lets you run quantum workloads, it's hardware agnostic. So what Microsoft have done is they have taken hardware from presently, I think, about 3 or 4 different actual quantum computer manufacturers and linked them into Azure. You pay your money, you add the provider, and then you can run quantum workloads on those computers. I don't think they're actually in the Azure data centers. I think they're just linked. But nevertheless, Microsoft has taken the view that given that they haven't got a quantum computer yet that works, there's no surface quantum, they are bringing other people's computers in. Pay-as-you-go model, because it's Azure, of course. Pay for what you use, all that sort of stuff. Very important to get your estimations right so you don't use too much and end up with a giant Azure bill. It's rather like job management. It's rather like working with an old school mainframe, a really old school mainframe, where you worked on the job during the day, you submit it at the end of the day, someone runs it overnight, and then hopefully in the morning it's finished and you spit out the result. It's a little like that. With Azure Quantum, they include an SDK for Q# and Python, which gives us integration to Visual Studio, Visual Studio Code, Azure DevOps. I've highlighted the SDK because it's really important. You saw the quantum circuit that I showed, the Hadamard test. Still don't know what it is, really. Nevertheless, it doesn't matter. As long as you know what it does, then Microsoft have implemented it for you in the SDK, along with hundreds of other quantum algorithms. As long as you can make the leap to understand that you need to do a Hadamard test and so and so and so and so and so and so, they're done for you. They're packaged up already in the SDK, which might put quantum programming within reach of regular people. Current model is it's a hybrid thing where the quantum code and the classical code run right next to one another. And what that means is that the quantum, the classical code can keep squirting data in, and the classical code and the quantum code can keep running. Previously, before it was hybrid, you had to package up the job, ship it to job management. It'd run it sometime. You get the result back. You do the next bit. And given that we're iterating all the time, it's a very slow process. But now they've done this hybrid thing where they're joining together with classical code and quantum code running next to each other. Simulators are vital when you're developing. You can't hit F5 in Visual Studio and have it go to a quantum computer, have it run, and come back to you. It doesn't work that way. If nothing else, in the quantum world, you can't stop the program and ask it for the value of that qubit. You can't put a breakpoint in and say, just stop there for a second, let me have a look at that, because it's quantum. The act of observing the state kind of locks it, kind of finishes the circuit, collapses it. So you have to run simulations, and the simulations do their best, and there's various different sorts to get things done. And the resource estimation is important too. Optimizations, Microsoft refers to these as quantum-inspired optimizations. So all the quantum computer scientists haven't just been tapping their fingers on the table, waiting for the engineers to give them a million quantum computer. They've been getting on with some other stuff. And optimizations are the use of quantum-inspired algorithms called quantum-style processing to try and get jobs sorted out. Q# is Microsoft's programming language for quantum computers. It's hardware agnostic, which is quite nice because, as I said, the current quantum computers are wildly different from one another. You don't just compile things to x64, you have to compile them for the computer you're going to, which is how it was like in the olden days. And it's a sharp language, so it's familiar to program. And you have C# and Q# next to each other in your projects, and you can work on them as you would normally. This is optimistic, but let's give it a go. This is a quantum workspace. These are quantum computing providers, IonQ, Quantium, these guys. They give you free money to use, which is pretty good. Look, $500 of free money. I've managed to spend 3 of that so far. Jupyter Notebooks is what we're looking at here. This is Jupyter Notebooks are a way of mixing code and documentation together in one thing. They allow you to run snippets of code in the web browser. So I'm just going to run this, which sets up some stuff. I'm going to simulate the random number generator on the simulator, and it is going to produce some ones and zeros. All right. I'm then going to connect to a quantum computing resource. And now, these are the actual targets that you can run quantum jobs on. And many are broken. Degraded, unavailable, degraded, unavailable. Many of them are simulators. There's the estimator here, is a simulator and all that sort of stuff. If you want to run it on an IonQ processor, you've got to wait a while. It's 1.5 million seconds. There's a Rigetti here Rigetti that you can run on. So let's have a go running on that. I'm going to connect to the Rigetti. The wind in the right direction. It will be happy. Okay. 5-second queue. All right. Yeah. Fair enough. Cool. And then I'm going to run the same program now on the Rigetti, or more correctly, I'm going to submit it, and then it will go into the job queue. And if we're lucky, it'll complete. Frankly, I doubt it. However, let's try. Oh yeah. So quantum factoring. Factoring is a very benign term for the end of encryption. What they're talking about here is breaking RSA public key encryption with a quantum computer. Now, Google had a go at this recently, and they came up with an algorithm that is pretty optimized for this. They did it, they claim, to figure out how long we've got with current encryption technology before a quantum computer can break it. Take 1 million qubits to break RSA 1024, and then the current IBM computer's got 48, so we're a way off. We need some exponential growth in the sophistication of quantum computers in order to get there. So we've got a while. The solution, they believe, is to have crypto agility, which means that as soon as someone breaks RSA 2048, we slot in a different encryption mechanism between the bank's website and your web browser, between your WhatsApp and your wife's WhatsApp, on the encryption inside your computer for the hard drive, because it's all the same stuff. It's all in RSA and public key cryptography, and it all becomes vulnerable as soon as someone gets 1 million qubits, runs the algorithm, and there you go. I can show you the estimator. We can run an estimator here. Oh, the job has succeeded. Oh my goodness me, look at that. The job has succeeded. Who knew? Did you see the lights flicker as the quantum things ran it? Quantum computer ran the job. So it's producing random numbers. Simple as that. There's the input. Here's the random number, and that's all it was there to do. And these are what could be described as proper, legitimate random numbers, rather than ones made up by an algorithm inside your computer, based on the clock and the serial number and all that, whatever they do to seed the random number generator. These are universal, at the very lowest level, random numbers. Let's give the factoring a quick go. This is the code we're going to try and estimate. So this is they've implemented Google's code to try and break RSA. This is a couple of different sorts of gates and qubits, and I'm going to submit it to the estimator. This will give us some dots to look at for a moment. It takes about 10 seconds. This will run because it is running a classical program. There we go. We can put the results into an easy to read format. Right, okay. So this is different sorts of quantum computer, as it would have different qualities of quantum computer, different gate types, different error rates. Top of the shop here. If you had a computer that was like this, you'd need 37 million qubits, and it would take 6 years to break an RSA encryption. What's more worrying, down here, you need a computer that's got 6 million qubits, and it'll take 7 hours. We need to get there. These are vast numbers compared to where we are at the moment in terms of actual qubits inside computers. But nevertheless, this is what the estimations are. If someone could build a machine that's like that, the CIA would have your hand off, and so would every law enforcement government around the world. So we also have quantum-inspired optimizations, which means things that use quantum-like functions to get stuff done. Believe it or not, loading containers onto a ship is way more complicated than you'd think. This is an incredibly simple example where they're just trying to balance the ships. They've got a number of containers, and they're trying to balance the ships out, so they put the same weight of containers on both. In the Microsoft Learn course, you go into this in some detail, and I confess I did understand it at one point. And this is what they refer to as an NP complete problem, which means it's a hard problem to solve with traditional computers. So they've implemented this model, and we can run it on a quantum-inspired algorithm, which will give us an answer. So we're going to load up some functions here. We have some containers and their weights. We're going to try and put on these 2 ships, and we're going to submit it to the solver. So there's some numbers in JSON format. Let's put them into a nicer format. Here we go. Container 0 went on ship B, and it may balance them pretty well. So we'll take that. Let's have one huge container. There we go. It's balanced the ship. Oh, it's right, eh? There's done a very good job of balancing the ships, frankly, but never mind. Just a couple of terms then. Quantum advantage is a job that we know a classical computer can do, and they've proven that a quantum computer can do it mildly better, hopefully wildly better. Quantum supremacy, which is a bit of a scary word, is something that a quantum computer can do that a classical computer could never do. You know, in the lifetime of the universe, it wouldn't be impossible for it to do. And we're not quite there with that yet. There's a talk of money. There's always money sloshing around these things. Yeah, billions. As soon as we start to get a large scale quantum computer, I think we'll see that number go up massively. Microsoft are pushing hard for a 1 million qubit computer, and that won't fit in your immersion heater. That's going to have to be on a chip or at room temperature, ideally. So you have to keep buying liquid helium. Huge changes are proposed if they can get it to work across healthcare, medicine, energy, better batteries, better solar panels, more food. Better batteries too. I guarantee it. the moment I put the money down on an electric car, some quantum guy comes along and says, I've got a battery that stores twice as much for half the weight and half the size. And you go, so...
Is there any overlap between what we're seeing with AI and quantum computing?
I read a thing yesterday where they're talking about using an AI in the classical loop to drive the quantum, and that sounds like the plot of any AI apocalypse film you've ever seen, doesn't it? Yeah, quantum AI. Oh dear, takes over the world.